Hello everyone, welcome to the recitation class for chapter 8 and the laminar flow part. Today I'm going to solve two questions for this concept, which is laminar flow in pipe flow. So the first question is a large artery in person's body that approximated is a tube of diameter 9 millimeter. So the tube means that the cross-section area and all over of that is the same and diameter doesn't change. Okay, so first I'm going to show you how it's based on the information that we have in this question, how we can write down where is the flow and from where to where we have the pipe flow. Okay, so first that's the pipe flow and the length of that is also given, and the blood has a viscosity. So in reality viscosity of blood is not constant, but it mentioned that has a viscosity approximately equal to 0.004 Newton second per meter square. Specific gravity is also given. Pressure at the beginning artery is outlet of the heart. So from one part you have heart here. Okay, the flow comes in to the artery and end up to the abdominal. So here is 0.1 and that would be your 0.2. Okay, the diameter of that is given, and also you don't know what is the angle of that, right? So you have to answer that during the solution, but for now you can assume that it's arbitrary and the angle is theta. So let's list the assumptions first. What are the assumptions here? First, the flow is a steady state. And you have to assume that, and you have to assume that the flow is fully developed, right? So it's outlet. After that, the blood flow is steady, is mentioned here. Actually it's pulsatile, it's right. The flow in the pipe, because of the heart, has a cyclic contraction and expansion, so this is going to be pulsatile velocity, but you can assume here that it's steady and you have a continuous velocity here. And since the artery is also after entrance to the artery, you are talking about the part that you have a fully developed part flow here. So also you can assume that it's incompressible and constant properties. What are the properties that you can assume is constant? It's like viscosity. As you know, viscosity of blood is not constant, changed with the velocity and also in different conditions in the body, but you can assume that for now because it's mentioned approximately is given. So what are the nouns here? List your nouns. First, the D of the pipe is given, is 0.009 meter, which is 9 millimeter total. What else? Length of the pipe is also given. Length of the pipe is 0.35 meter. What else? The mu of the blood is given, 0.004 Newton second per meter square. Pressure at the velocity of the blood is given. V of the in is constant and 0.2 meter per second. So V in is 0.2 meter per second. What else? It mentioned that the pressure after the heart is 120 millimeter Hg, or Hg means the mercury. So the pressure is almost given to you. So P at 1 or P in is given, which is 120 millimeter of the mercury. We'll find out. And also Sg is given, which is the specific gravity for blood, and you can assume that is 1, means that the rho is the same as rho of blood. Okay, so what else you have to know? If you assume that this is 0.2, right, then from 1 to 2, in 0.1 you have P1, V1. Also area is constant all over that, and that's your artery, right? You have theta, and if you assume that Z is here, right, so Z2 is going to be 0, but Z1, if the length of that is L, then Z1, which is here, going to be Z1, and Z1 is going to be L sine of theta. For now you have this information, right? What else? The P, D, V, and yes, these are all given information, right? But what is asked? It asks you that determine the pressure when the artery carries blood to the abdomen. So here means that P2 is asked by you, but in different condition. So first is standing, right, upright. B is laying down, and for C it's just you can answer when you answer part A and B, you have to know that which one is the because of gravitational term and which one is due to viscosity effect. We'll talk about later. But A and B are going to be different based on the different theta, right? So we'll find it out, the equation first in general, and then apply theta, because if it's standing upright means that theta is going to be pi over 2, and when it's laying down then means that theta is going to be 0, right? So we'll apply it later when we find out the equation for the P2, okay? But before any of things like that, you have to find the P2. But before that, you have to find out that is the flow laminar or turbulent. You have to answer that because you don't know the flow is laminar or turbulent. If the turbulent is, then the equation going to be different. All the flow is all the equation that you find out in the part of laminar is only valid for the laminar, right? So it's not for the turbulent flow. You have to check it first. How we can do it? Find the Reynolds and compare with the critical Reynolds, right? Reynolds is rho VD over mu. Then also rho of the blood is going to be rho of water times Sg times velocity of the in times diameter of the artery over mu of the blood, right? If you have replaced this, then it's going to be 999 kilogram per meter cube for rho of water. Sg is going to be 1, V in 0.2 meter per second, right? That's the velocity, and diameter is diameter is 0.009 meter over mu of the blood, which is 0.004 Newton second per meter square. By answering this, by calculating these numbers and do the solution, the Reynolds would be 450 in total. Okay. Okay, so you find the Reynolds. What's next? Compare that with the critical Reynolds. Critical Reynolds is 2100. That is your Reynolds critical. Then after that you will have a transitional. But 450 is much less than the 2100, and which is your reference critical, and you can say that the flow is laminar. Okay, so you have to check it, even though that the question is mentioned that the flow is laminar. If the question told you that the flow is laminar, I'm telling you that the flow is laminar, you don't need to check it, but in general you have to check it to make sure that the flow is laminar, right? For now you don't know. Actually you have to know that the flow is not laminar exactly when in reality after the heart, because the velocity is high in the artery, that the blood comes exactly after the heart, in reality is not laminar. It's a little turbulent, but after that is going to be laminar and going to be fully developed, but is only for a small part of the artery. But here we are talking about the part that the flow is laminar based on the velocities and all things. Okay, what we should do, we should apply the conservation of energy, right, to find P2. That's the answer that we have to answer this question, that what is P2, right? So write down the conservation of energy. The conservation of energy is P2 over gamma plus alpha 2 V2 squared, right, over 2G plus Z2 is equal to P1 over gamma plus alpha 1 V1 squared over 2G plus Z1 plus HS minus HL. Shaft work head and loss head, right? Head loss is HL. Okay, that's your equation. But what do you know about the pipe flow when the diameter doesn't change? And we talked in the previous video about the alpha 1, alpha 2 are the similar. Also V1 squared, V2 squared are similar, and by conservation of mass you can find out that alpha 1 is equal to alpha 2 and V bar 1 is equal to V bar 2, and you can get rid of these two terms and cancel out those, right? You can cancel out these two, and also you don't have any work here, so HS is going to be 0, and you assume Z2 is 0, so you can assume that this is also 0, right? Z2 is 0. P1 and P2, you have P1, you have gamma, but P2 is asked you to find out, and the only term that you don't know and you have to find it out, because Z1 is also L sine of theta, right? But HL still should be fine, right? So for now, we rewrite this equation as here. When we make it simple with P2 over gamma is equal to, we get rid of these two terms, is equal to P1 over gamma plus Z1 minus Z2. We don't care about it because Z2 is 0, only Z1 should be here, so Z1 and minus HL, which is your head loss, right? You write it down here, and if you multiply all sides, by gamma, then you will have P2 is equal to P1 plus gamma. Instead of Z1, I can write that L sine of theta, right, minus gamma H, right? That HL is your head loss. Okay, so what we know here, that L is given, theta, it depends, for part A and part B could be different, but it has to be given because you have one own equation, and P2 is the only thing that is asked for. P1 is given, P1 is 120 millimeter Hg. Okay, so you can find it out by multiplying 0.12 meter, which is 120 millimeter, times the gamma of the mercury, which is 133 kilonewton per meter cube, right? If you find it out, then the P1 is going to be 15.96 kilopascal. Okay, so for now you find out the P1, and also the gamma for the blood is equal to rho of the blood times G, right? But rho of the blood by itself is rho of the water times Sg of the blood times G. Rho of the water is 999 kilogram per meter cube times Sg is 1 and G is 9.81, right? I'm just writing that and making finalize what exactly is needed for finding P2. Okay, so this is another thing that we have to replace here as a gamma, which is 9800.2 kilogram per meter square second square. Okay, so what else? The final thing, theta has to be finalized when part A and B going to be solved, when we find out what is the direction of the pipe. L is also a constant number. We'll multiply that by gamma, we find it out. But what about HL? Okay, so for HL, as we talk in the teaching part, okay, so HL has two parts. In the part of HL, you will have the head loss, which is equal to HL of major and HL of minor. So we have two parts in the head loss. One is major loss and is minor loss. So minor loss, as we talk in the class, is about the curve that you have, elbow or any valve that you have in that part. But since you have a straight pipe here, this is going to be 0. Okay, this is only a straight part, and it doesn't mention the thing that you can assume is 0, but you can assume that is 0. Okay, because here you have a straight pipe, and then you can say that HL is only HL of major. Okay, so what is that equation for it? Since that's the flow in major, as we talk in the class, this is going to be F, which is your friction, times L over D times V squared over 2G. Okay, that's your equation, and since that's laminar flow, then this is going to be 64 over Reynolds times L over D times V squared over 2G. You replace the L because of this laminar. Okay, then in general HL could be found out as 64 over 450, which is your Reynolds number, times L, which is 35.35 meter, and the D is 0.009 meter. Okay, just replace for L over D, and velocity is 0.2 meter per second square over 2G, which is 2 times 9.81. By calculation, you will find out that HL is almost 1.3 times 10 to the power of minus 2 in unit of meter. Okay, so you find out what is the HL. Let's use the equation that we find out here as I, and replace all the nouns and find P2 based on the parts. Okay, so for part A, it gives you that the artery is standing upright, right? If it's upright, then theta would be pi over 2, right? So it's going to be like this, and theta would be pi over 2. Okay, then in equation 1 for I, you will have P2, which is equal to P1 we find out that is 15.96 kilopascal. Don't need parentheses here. Plus we have gamma L sine of theta. Gamma is, we find it out, the gamma is 980 9800.2 times L, which is the length of the artery, which is 0.35 times sine of theta. That theta is 90 or pi over 2. Okay, and also we have to make it kilonewton because we want to have a kilopascal term, right? So we make it over 1000 to have a kilopascal here, and minus gamma again, which is 800.2 over 1000 again for the kilopascal term, times HL, which is, we find it out is 1.3 times 10 to the power of minus 2, and again that's kilopascal. Okay, so what's the difference here? That we, based on A, we put sine of theta is equal to pi over 2. So if we find it out, P2 is going to be 15.96 for P1 plus the second term, which is here, which is 3, is going to calculate it as 3.43 kilopascal. Excuse me, and minus the third term, which is 0.11 kilopascal. Okay, and the answer would be P2 almost equal to 19.3 kilopascal. Okay, but also part C asks you a question that indicate how much of the pressure difference is due to elevation or gravitational effects, and how much of that is due to viscous effect. Okay, so viscous effect means that the last term means that the term that you find it out here, so that's because of viscosity effect. And the other one that you have L sine of theta, which is because changing because of the direction of the pipe versus the horizontal direction, is going to be the effect of gravitation. So that's going to be your gravitational. So we answer part A and also half of part C, which is showing that which one is from gravitational effect and which of those is from viscosity effect, right? So the term that loss, only loss is negative term, that you have pressure drop. You have one pressure drop from P1 to P2, and delta P is going to be answer that that's the moving forward force that makes the flow passes, right? That's come from the pressure difference comes from the heart. Contracted, and because of the contraction of the in the heart, you have high pressure, and that's P1, and P1 is going to change to P2 from high pressure to low pressure, and that's why P2 is going to be your from high pressure to low pressure, and the pressure changes, and because of that velocity also changes, right? But that's here you will find out that how much of that is going to be lost by viscosity and how much of that is going to be added because of gravitational effect. So here you know that the P2 by itself, okay, if you didn't have any gravitational effects here, means that the flow is in a horizontal pipe, then P1, which is here, that's your P1, right? That's the pressure at heart. And also if you don't have any gravitational effects, then only because of viscosity you will have loss of energy because of the pressure, and you have a pressure difference. Okay, so the final pressure, that is output pressure, is less than the P1, which is P2 is less than P1 if you didn't have gravitational effect. So that means that when the heart is in top of the body, close to the head, in the chest, Then for distribution of the or cardiovascular system that you have for distributing blood inside of your body, and when it's going to bring your blood into your feet, the gravitational effect helps, right? That's why when you suddenly standing up, because the blood should come into your head, and that time the gravitational effect, it has a negative sign, right? Because it's going to be in an artery that brings the blood into your head. That's why you have rush head, or sometimes you have dizziness. That's because of that heart cannot, at the same time that you are standing very fast, and it doesn't expect that you are going to stand. It took time for it to give the high pressure and compensate for the amount of gravitational effect. That's going to, because you are standing right now. Okay, these are all different things that may be the different arteries based on the direction of arteries, but the gravitational effect is here, and you mark it down that how much of that is going to be added to output pressure because of the gravitational effect. But in part C, that would be more interesting to know that if the flow is in a horizontal part, so in part B, it asks you that if that's horizontal or it's laid down, the artery is horizontal versus the G, then means that the flow here, G direction, if that's a G direction, right, and the flow is in this direction, then the effect of gravitational is zero. Okay, and at the same time, if the flow, if the artery goes up, it means that up or down in direction of G versus the heart, then absolutely that would be negative sign. But here in this part, it asks you that if the artery is laying down, it means that standing, not laying down means that it's horizontal, right? So you don't have any gravitational effect. So no gravitational effect. But the same analysis, right? What does it mean, the same analysis? You can rewrite the same equation that you have in the previous one. So P2 is going to be P1, which is 15.96 kilopascal, plus 0, because this is going to be a gravitational effect, is going to be 0, minus, again, viscosity is by itself another term, and it has to be there, so it's going to be your viscosity effect. Nothing changed, only you make the gravitational effect 0. Why? Because if you see the equation that you have here, in the equation you have L sine of theta. Sine of theta, theta is 0 here, then it's going to be 0. That's why if it's 0 there, it's going to be changed based on the direction that you have. So P2 is going to be, by doing the calculation, you will have 15.85, right? It means that the input pressure, which is P1, is higher than P2, and it means that part of the pressure, because the velocity average is the same direction, and also it's a horizontal pipe, so you don't have any gravitational effect here, but you have loss because of viscosity in the artery, right? That's why the P2 is less than P1. And we already answered part C, that which one is from gravitational effect and which one of those is from viscous effect. That's the first question. It's easy question and help you to know more about the way that we calculate the losses, head loss in laminar flow. Here is another question that is a little confusing maybe. By doing assumption, you need more assumptions there. So it's a liquid inside of the maybe that's a tank, or maybe whatever it is, but the flow is at rest here, right? And because of the syringe is going to goes up, then the fluid, which is going to be a liquid, on a liquid, is going to go through this pipe and comes to from this pipe to a different diameter pipe, and inside of that, right, is going to move it here. So a steady state assumption is still valid here. If you write down what is the assumptions. First of all, a steady state. The second is incompressible, and third is constant properties. Constant properties means that viscosity and mu is not going to change. Okay, so we'll find out what is these assumptions. These are my assumptions. What else? If you do the numbering on this part, because it asks you that when the Q is going to be maximum, and means that it's going to be maximum when the pressure here is equal to vaporing pressure. So vaporing pressure is also given, right? So you have pressure here, and you want to know that if I make the pressure here equal to vaporing pressure and make it higher and higher, then the Q is going to be maximum. So we want to make the Q maximum and find out what is the Q maximum. So here is going to be my 0.1, and here is going to be 0.2. We need that because diameter of the pipe here to here is going to change, right? And also 3 is on top behind the syringe, the closed part here. And pressure here is not pure atmospheric pressure because it's inside of that, and it's going to be vaporing pressure. But at 0.1 you have is atmospheric pressure. So after numbering, let's write down that what we have and what we know here. First, P1 is given is P atmosphere and is 101 kilopascal, almost. Okay, P1 is given. What else? V1 is not given. Alright, we don't know how much is the velocity of flow. Here velocity is 0 and it's maybe huge time, but velocity comes in. So we have V1 here, but P1 is P atmosphere. Okay, we don't know what is V1, but we know what P3 at 0.3, P3 should be almost equal to vaporing pressure, right? It's given as 12 kilopascal. Can we assume that the velocity at here is going to be 0? Since the velocity at V1 is here, and you can see that the diameter is 10 millimeter versus 0.25 millimeter. So 10 millimeter over 0.25 is huge difference. Then you can assume that the velocity V1 is a reasonable velocity. You can assume that V3 is highly smaller than V1. Then you can assume V3 is going to be almost 0. If not, you cannot solve that question. So that's why the fluid mechanics is based on the assumption, and you have to always ready to apply assumptions whenever it's needed. Okay. There is any work here? No work. Then HS is going to be 0 in your equation of conservation of energy, right? And what else? That we have a loss there, right? Head losses. So head loss, which is HL, it has to be, that's a multiple pipes, right? Pipe 1 and pipe 2. In multiple pipes, the head loss that you have from here to here, it has to be added to the second head loss, right? So it's going to be HL from 1 to 2 plus HL 2 to 3. That's why we put number 2 here, right? Because the head loss is going to be different by the different diameters, and the pipe its shape is changing, right? So then you have to say that Reynolds number is going to change from part to part. Then head loss is going to be changed, right? You only need to say that the total head loss is going to be summation of the head loss 1, part 1 of the pipe, and second part of the pipe. Okay, so all is ready to apply the conservation of energy. Okay, if I apply conservation of energy, and again I will assume that the V3, the alpha part is equal to alpha 1 is equal to alpha 2. So this is going to get rid of the alphas, because if alphas should be there if it's needed to be calculated or needed to be there. So there is nothing talk about the alphas here. You can assume the alphas are the same, but velocity average is not the same. Okay, so if you write it down the equation and get rid of the terms that you don't know what is that, or those that are zero, so the equation of energy equation is going to be 2g. So alphas are the same and equal to 1. I can assume that to equal to 1, or because I cannot cancel out these two, but I can assume these are 1. Okay, and also raw water is given as 999 kilogram per meter cube. Okay, so V3 to the power square, V3 square over 2g plus Z3, it has to be equal to P1 over gamma plus V1 squared over 2g plus Z1 minus head loss. Okay, that's the whole equation. But what we know, we assume that V3 is going to be 0, right? This is going to be 0, and we know that the head loss is going to be summation of two terms, HL122 plus HL1223, right? We also know that this is going to be replaced by HL. What else? If I bring the P1, keep the P1 here and bring the HL on the other side, right? Then we have P1 minus P3 over gamma plus Z1 minus Z3 minus V1 squared over 2g. I bring this to other side. Has to be positive, because that's going to be P1 minus P3, Z1 minus Z3, and this is going to be positive, but HL comes the other side, so HL is going to be positive now. Okay, so also HL is HL122 plus HL223. Perfect. So as we talk in the class, HL1 is going to be F, a friction factor of 1,2 L12 over D1 plus V1 squared over 2g, right? And the second term here is going to be F223 L23 D2 D2 or D3 are the same, so V3 squared over 2g. That's the second term, right? But we found out that we assume that V3 is going to be 0 because of this is also not given in the equation, but we can assume that. And in the exam I will tell you that okay, you can assume V3 going to 0 or not. Don't worry about it. That's based on experience that I have in the solving this type of question in the fluid mechanics. But these are also part of the assumption that you can assume it. So this is going to be 0 because V3 is going to be 0, right? Or negligible. But what about the second part, the fluid laminar? And if you see that V3 is going to be 0 and V1 is not much higher than that, so we can assume that the flow is laminar here, and this is going to be 64 over Reynolds times L12 over D1 plus V1 squared over 2g, right? I can replace, that's not plus, that's multiplication, right? So this is going to be 64 over Reynolds L12 over D1 times V1 squared over 2g, right? What about Z1 minus Z3? Z1 minus Z3 is going to be your delta Z, and also you have P1 as P atmospheric pressure. What do you want to calculate here? What is unknown? Check your list of known and unknown. Is V1 given? No. So V1 is not given here. But the rest of the terms, Z1 minus Z3 are given, P1, P3, you know P3 because it's given, and P1 is the atmospheric pressure is also given. Delta Z is also in the figure, is obvious that is 0.12 meter. And here in 64, Reynolds is rho v d over mu, and these are given, d1 and d2, all the pipe diameters are given in the figure. So Reynolds in also rho mu, because Sg is given for the liquid, then rho is given, d1 is given, v1 is not given, so you have again the same unknown parameters v1 and v1. 2g are the constants, so L12 is also given. All terms are given except v1. You have one equation, and if you rewrite based on v1, you can answer that what is your v1, right? So we can do it and rewrite the equation here, that by replacing this constant thing that we find and rewriting the equation, we have finally the H loss, head loss, which is 64 over Reynolds number times L over D, again is 1 over 1 to 2. I'm just get rid of 1 2 because we only have one term. So v2 v1 2 squared over 2g, these are all d1, is equal to, if I replace Reynolds with rho vd, then it should be rho vd and mu comes up, then L over d, then v squared over 2g. Okay, so it's going to be 2 and 64 going to cancel out each other and going to be 32. So 32, bring mu here, L v over rho g d squared. Okay, so I'll just make it, the last term is easier based on the known term that I have. So here rho is given, mu is given, L, G, D, 32 is a constant, only velocity is not given, which is velocity at 1, right? So bring it to the equation that you have, P1 minus P3 over gamma of the liquid plus delta Z minus V1 squared over 2G. It has to be equal to this term, 32 mu L 12 V1 squared over rho d1 squared g. Okay, I'm going to first calculate this part. It has to be 32 times mu is given 9.210 to the power of minus 4 times L1 to 2 is 0.1 meter, right, is also given, and V1 is not given, right? This is also doesn't have any squared here because one of this V is going to be cancelled out by this, right? So it's going to be V1, and this is V1 is unknown, and rho is 96.96 for Sg, and rho of water is 999. So multiply by 999. D1 is the diameter of the, if you check the figure, is going to be 0.00025 squared because it's a square, and multiply by 981, which is your G. Okay, if you apply use the calculator and calculate this part, this is going to be 5V1. I'll put the equal here. What else? P1 here, P1 is going to be 101 is given, atmospheric pressure, minus 12 kilopascal for P3, that is vapor pressure, and also you have to multiply by 10 to the power of 3 to have Pascal, over gamma is 0.96 or Sg times G 9.81 about multiplied by 999, which is your gamma of liquid, is going to be 9.8 times 10 to the power of 3 kilonewton, or newton, because you multiply that already in 10 to the power of 3 newton per meter cube. Okay, plus delta Z is given as 12 meter, 0.12 meter, and also the last term is minus v1 squared over 2 times 9.81. Okay, so if you see here, you have to solve an equation to find out what is v1, because v1 squared is here and v1 another term is here with the power of 1. You cannot just add these two together, right? So you have a second order equation that you have to find it out. So by finding the answer of that, this is going to be 9.46 meter, okay, plus 0.12 meter, that is this one, and here is going to be minus 0.05 v1 is equal to 5 v1. This has to be squared, okay? So just multiply that by 100 over 5. If you multiply each side in 100 or multiply by 20, then this is going to be 100 and this is going to be 1. Then bring v1 squared to other side, then you will have v1 squared plus 100 v1 minus 186.8 equal to 0. Okay, if you solve that for using find the roots of this equation, one of the roots are negative, but v1 cannot be negative. Never. It's always positive. So you have only one of those are acceptable, and it's going to be v1 equal to 1.83 meter per second. Okay, that's the answer for this equation, but the other one is negative, and if you don't remember, you have to find delta, which is for an equation that you have as x squared plus bx plus c equal to 0. You have to find the roots as at first delta, which is b squared minus 4ac, and then the root is going to be minus b plus negative square root of delta over 2a. That's the roots. So one of the roots are minus b is negative minus the square root of negative, and a is also 1. Then one of those are negative, you don't need that, but the second one, which is minus b, which is minus 100, plus the square root of delta that you calculated over 2a is going to be equal to 183. Perfect. So final thing is that finding q. Q is going to be a times v, velocity, right? So a 1v1 is going to be your answer. So a1 is pi over 4d1 squared, and v1 is also find it out here. Then q is going to be pi over 4 times 0.00025 meter squared times 1.83 meter per second. v1 is going to be 8.9 times 10 to the power of minus 8 meter cube per second, or 89 millimeter cube per second. That's your answer for Q. So you saw that how we solve this type of equation. First, you have to, anytime that you need to know that which equation you have to use, laminar turbulent, you always have to apply. You have to find the Reynolds number. Then when you find out what is the Reynolds number, then you can say that it's laminar or turbulent. And then when you find it out which one is that, then you can use the equation that we provided in the chapter 8. So I hope you enjoyed the class, and this question and recitation helps you to solve the question that you have in the homework. But we have to stop today, and in the next class I will talk about the immersed body and the flow over immersed body. That this is your chapter 9 and the last chapter in this class. and you will have one question in the exam, but that would be a bonus question. You don't need to be that much worried about that, but if you want additional points, that would be helpful for you guys. Have a good one.